Hey everybody, Dr. Powers here. We're going to look at some problems looking at confidence intervals using the normal and the t-distribution. So confidence intervals related specifically to the population mean. I'm going to go through three problems here and look at how we can use some formulas in Excel to calculate this stuff. And I'm going to use the go through the formula, as well as I'm going to use the kind of shortcut. So let's take a look at this first one. The GPAs of students at a certain school follow a normal distribution with a population standard deviation of 0.52. So we are told that the population shape is a normal distribution, and we are told the population standard deviation is 0.52. Therefore, we are allowed to use a normal distribution to model the sampling distribution of the sample mean. Now, this is something that never happens in real life, but in a problem like this, you're allowed to. In real life, you just use the t-distribution all the time because we never know the population standard deviation. How could you know the population standard deviation and not know the population mean? That doesn't make any sense. At least that's my opinion. My opinion is when calculating when estimating the population mean, just use the t-distribution all the time. At any rate, here we are. We're going to use a normal distribution because we have these two conditions met. The population is normally distributed and we know the population standard deviation. We have the GPA of 12 randomly selected students given right here. We're going to calculate a 98% confidence interval for the mean GPA at this school. So I'm going to first calculate this using the formula. Okay, we're going to go and find these 5 numbers, and they're going to be the ingredients to calculate a 98% confidence interval. First thing is the sample mean. We need this because this is going to be the middle of our confidence interval. The x bar, also known as the sample mean, we can get that using the average function. Average, parentheses, and I'm going to grab all of these numbers. Next, the standard deviation. This is because we're going to just use 0.52 because that's given to us. I'm not calculating the sample standard deviation because I'm given the population standard deviation is 0.52. Okay, sample size, this is easy, this is 12. We're given that as well. If you wanted to use Excel, I'll show you the formula. It's going to be count. Count, parenthesis, and then I'm going to count all these numbers. Excel can do the counting for me. There's 12 of them. Now, T-star. T-star is going to be found using, not T-star, Z-star. Z-star is found using a normal inverse. So this is going to be norm.inv. And I'm going to find the, now I want to use, because I want to find where's the cutoffs for the middle 98%, that means there's going to be 1% in each of the tails. So what I'm going to do is actually, I'm going to use do 0.98 plus 0.98 divided by 2. It's 0.01. It's the lower tail has 1%, the middle has 98%, and the upper tail has 1%. So this is going to be the cutoff for the lower 99%. That makes sense? The mean is 0 and the standard deviation is 1 because this is from a standard normal distribution. And finally, the margin of error. Margin of error is the standard error, which is standard deviation divided by square root, SQRT, the square root of the sample size, times Z star. All right, so it's the standard deviation divided by the square root of sample size. Those two together are what we call the standard error of the estimation, or the standard error of the mean. And we multiply that by Z star. That's how many standard deviations, or that's how many standard errors we go on to the left or the right. that makes up our margin of error. So our lower bound, or call it L bound, and upper bound. The lower bound is going to be the sample mean minus the margin of error, and the upper bound is going to be the x bar plus the margin of error. So what can we say? We would say we are 98% sure that the mean GPA of students at this school is within this interval from 2.4 to 3.1. You want to be careful when interpreting it. You don't want to say I'm 98%, or there's a 98% chance that the GPA is between 2.4 and 3.1. That implies that the GPA is a random number, and sometimes it's in between those and sometimes it isn't. Some people are more of a stickler about this than others. I'm more of a stickler than some. The GPA is unknown to us. That doesn't mean it's random. It's just unknown. It's a fixed number. It exists and it's fixed, but we just don't know what it is. So there's a chance our interval is wrong, a 2% chance our interval is wrong, a 98% chance our interval is correct. And when I say correct, I mean that it correctly bounds the the true mean. As far as stats goes, I've done it correctly. That doesn't mean that it actually, there's still a 2% chance that I am not bounding the true mean. All right, so let's see how we're going to do this. The faster way to get the margin of error is to use a formula. It's confidence.norm. And the things I need to put into this are the alpha. Alpha is the probability out in the tails total altogether. Since it's a 98% probability, I'll just do 1 minus 0.98 to give me my alpha. Oops, comma. Standard deviation, that's 0.52. And the sample size is 12. Those are the numbers that I put into this formula. I'm going to pause here for effect, hit enter, and I'm going to get the exact same number, 0.3492, 106. So you can get the margin of error by using that formula and cut out all those middle steps. All right, let's take a look at another problem. So I'm interested in how many unpopped kernels I'll get on average from Quickie Pop microwave popcorn bags. So I do a little experiment. I'm going to microwave 7 bags of popcorn, and I record my data. I get an average of 15.36 unpopped kernels and a standard deviation of 4.623 kernels. And we're going to, so if I was doing this like really properly, I'd have to verify that my data distribution is approximately normal, because it's a very low sample size, and for me to use a t-distribution, I'm going to need to be pretty okay with assuming a normal distribution for my population for this small of a sample. If my sample size was much larger, I'd be okay with a skewed distribution. So we're going to assume a normal distribution roughly for my data distribution. Okay, so I have the sample mean, the sample standard deviation, but I don't know anything about the population, so I'm not going to use a z interval or a normal distribution. I'm using a t interval. So I'm going to calculate a 90% confidence interval to estimate the population mean. Here's what I need to get. Okay, so once again, I'm going to get these numbers, x bar, the sample size, and that is going to be, actually, I'm going to add another little okay. X bar, the sample mean, that's 15.36. Standard deviation, that's also given, 4.623. That's a sample standard deviation, not a population standard deviation. So we have the sample size, that's 7. Alpha I'll say equals 1 minus 0.90. It's 0.1. That's the significance level for this. It's 1 minus the confidence level. T star is going to be found using the t distribution. I'm going to do t dot inv.2t. two-tailed t critical t value. For this function, I give it the probability that's going to be out in the tails. It's going to be my alpha. My degrees of freedom, which is 7 minus 1. You can just type in 6 if you want to. And this is the critical t value. That formula that I just put in, it's specifically for a two-tailed critical t value. So it does the job of dividing the alpha by 2 and all of that. You just have to give it the alpha value, the total probability you want out in the tails, the two tails combined, and it'll do the rest of the calculation for you. Margin of error is calculated as the standard deviation divided by the square root of the sample size, once again, and I multiply this times t star. It's the same formula, except instead of the population standard deviation, we put in the sample standard deviation, and instead of a z star, we put in a t star. But it's very much analogous to what we did in the previous problem. That's my margin of error. So my confidence interval is going to be wide, but that's because I have a small sample size and there's a large standard deviation, right? And I'm doing a 90% confidence interval. All of these are going to lead to a pretty wide interval. My lower bound, upper bound. For my 90% confidence interval, my lower bound is going to be the sample mean, x bar, minus the margin of error. Upper bound is the sample mean plus my margin of error. Look at that. Now, we can do this also using a formula that's built into Excel. It'll get me that my margin of error, and it's equal to confidence.t. I give it my alpha, 0.1, my standard deviation, 4.623, and my sample size, 7. I don't do this the -1, it does that for me. It's going to calculate that exact same number, that exact same margin of error, and you can just go ahead and add or subtract that from my sample mean. So you can see that formula does some of the work for you. It's nice. You can skip a couple of little steps using that formula. I should say function, not formula, but I think Excel mixes the two words pretty casually. Now we want to estimate the GPA of students at another school, but we do not know the shape of the distribution of GPAs. We have sampled 36 students, so here's our data. I'm not given any population or any sample statistics. I want to just estimate the population mean GPA with 95% confidence. So we're still going to go through and get all of the same info. X bar, we're going to need that. Standard deviation, we need the sample size. We're going to need, I'll put alpha here, and we're going to once again use a t star and calculate a margin of error. And then we're going to get our lower bound and upper bound. We'll go through and get all of that stuff. Okay, sample mean is easy. That's using the average function. And I just select this whole big mess of things. I call them things. They're numbers. Standard deviation, stdev.s. Remember, it's a sample standard deviation, so that .s is important. And let's select them all. Nice. All right. Sample size, I already know it's 36, but I'm going to just, I have to use equals to do a formula. Count. It should give me the number 36. And alpha. Now this is going to be 1 minus 0.95. Of course, it's 0.05. So t star is found using the t.inv, 2t. That's again a two-tailed critical t value. And the probability is the alpha, just as before. Degrees of freedom, sample size, -1. I mean, now that we have all those other stats, we just go through the same exact way that we did previously. Margin of error, standard deviation, divided by the square root of the sample size, multiply that by t star. That's our margin of error. Lower bound is going to be 3.25 minus the margin of error. Upper bound, 3.25 plus the margin of error. And just to remind you how to calculate the margin of error using the formula, it's equals confidence.t alpha standard deviation sample size. Nice? Very nice. Again, we would interpret this confidence interval, we'd say we're 95% sure that the mean GPA of students at this school is within the bounds 3.12 to 3.38. Of course, there's a 5% chance that interval does not capture the population mean, but there's 95%. We're 95% sure that it does. That's a confidence interval for you. Okay, well, I hope this has been helpful, and I hope you do really well on these assignments. Okay, bye-bye.